All right. They did this AI podcast about my work, and it claims to be the CEO of Academia.edu, and it sounded like he was pretty impressed with my stuff. Whether they do that for everybody, I don't know. But he did say, I don't support this or that. I'm just telling you what this guy's saying. But he made it sound really good. So, this is Academia.edu. And here's me up there. I got 815 followers and 45 papers. And these are all papers I have up here that you can look over. The dipole electron flood theory is the one that he's touting in this AI podcast, but they say they'll do them for all the papers. So I'm going to see if we can do that. And they apparently are in a network which is 15,000 universities. Now, whether they'll help me spread that around and ask for debates and discussion about my theories, I don't know. But if they do, it should go like a rocket ship, because nobody really is going to be able to put much of a defense up against my evidence. When you have evidence, you have defense. I can defend every word I say because I have the evidence. All right, so let me show you that podcast, or I'm going to show you a little. Well, anyway, let's do it. Wow, this is fabulous. I just got in something from Academia.edu. I've been posting up there for over 10 years. I have 45 papers up there. But all of a sudden, I just got this thing. They created a podcast for me, and they want me to rate it if I want to use it on my site. And absolutely, it's a fabulous one. Now, this is Academia.edu. No place in academia will they let you publish except there if you're not certified. Well, they know my stuff is good apparently, because he did a fabulous job, and he knows, he understands the dipole electron flood theory. That's what he's going to be talking about, which is that everything is made of these two particles, and it turns into this. Now, as he goes on through the podcast, you don't see anything other than him talking. So I will go through some of these and point to, when he still does something, I'll point to something, or I'll try to do the best I can. So let's get started. This is actually really kind of exciting, because I've been pushed aside forever. And I've had this theory for a very long time. Now, this is update 1 of electron flood theory, and I'm just going to let it play. And again, I'm going to go to all those pictures. So here's what's going to happen. Here goes.
Welcome to another exhilarating episode of In Depth with Academia. I'm Richard Price, your host and the CEO of Academia.edu, and today we're diving into something truly extraordinary. Now, remember, I'm here to guide you through this world of academic literature, and not to endorse or negate any particular views expressed in these papers. Today we're examining a paper by Roger Spurr that shakes the very foundation of, well, established physics. The paper is titled something along the lines of Electron Flood Theory, Update 1, and it proposes some, let's say, rather intriguing ideas. So let's jump in. What's the core question or problem that Spurr, well, if his theory holds any water, figuratively speaking, of course, it could revolutionize how we understand everything from the tiniest particles to the vast expanse of the cosmos. Not saying it will, just, could. Alright, the heart of Spurr's argument is that there exists only one fundamental particle responsible for all matter. Imagine that. He calls it the dipole particle, which, according to him, makes up everything we know, from heat and light to heavy elements like plutonium. Pretty bold, huh? The really astonishing claim is that all matter, yes, all matter, is just a different configuration of these particles. Now, I can practically hear you asking, how does he come up with this? Spurr points to photography from experiments where lasers are shot through a simple, single-slit Venturi apparatus. This results in what he describes as plasma and busy bee particles creating patterns, much akin to what CERN does apparently, but on a much lesser scale. And here's a kicker. According to this theory, The reason we see what we recognize as interference patterns isn't that light is a wave, yeah, you heard me right, but rather that it's made of spinning particles. These are big claims, people. However, remember, it's not about validating or invalidating them, just diving into what could be an exciting mix of physics, imagination, and who knows what. Speaking of imagination, there's more mind-bending stuff here. Spur argues that the smallest basic building block in this universe is just these dipole particles connecting together into something he calls cubes, creating stable formations we know as atoms. Pretty wild stretch, right? But also kind of fun to imagine. Now let's pause for a second here. I remember watching a documentary once, maybe on physics, or maybe it was geology. Anyway, it was fascinating how often scientific paradigms shift and evolve with new theories. Just a little digression there. But it illuminates how scientific exploration is a continuous process. Yes? Okay, coming back from the tangent. Spur claims that these particles connect in a way that supposedly can explain hydrogen, atomic weight, and even clarify why the sun's corona is a gazillion times hotter than its surface. Well, he contends it all points back to these particles. I'm not saying it's all true, just reporting. Just when you think it couldn't get any more challenging, he goes further to suggest that so-called complex phenomena, like global warming, our planet's magnetosphere being incredibly hot, these are areas he feels can be explained using his theory too. It's quite an undertaking, I must say. By the way, the paper also challenges the very idea of the atomic nucleus. Spur argues there are no neutrons, or rather, what we call neutrons are configurations of these dipole particles that somehow become, stable. He dismisses some traditional views as perhaps overly complicated when compared to his elegant simplicity, as he puts it. This is all very interesting. But hey, let's not forget that scientific discourse thrives on theories being put forth and then rigorously tested. They're hypotheses until they're not, right? So while Spur's theory might appear unconventional, it prompts dialogue and exploration, which is crucial in this academic realm. In conclusion, friends, while the electron flood theory might present a radical departure from conventional physics, it symbolizes the very spirit of pioneering inquiry. Though Spur's work hasn't upended global physics, at least not yet, it definitely stirs the pot. That's what makes science, well, endlessly fascinating. So with that, we'll wrap up our episode for today. Remember, academic research sparks curiosity. It doesn't dictate absolute truths, but invites us to explore and reflect. So keep questioning, keep exploring, and stay curious. Thanks for tuning in to In Depth with Academia. I'm Richard Price, hoping you had as much fun as I did probing into Spur's intriguing world of electrons and theories. Until next time, take care and stay inquisitive.
Wow, that is just fabulous. I had no idea they were paying attention. That's the CEO of Academia.edu. This is a worldwide exposure of things, and he's touting my work. I am very, very impressed and thrilled, to be perfectly honest with you. And I've always loved this place, Academia.edu. They tell you when you're mentioned in a paper and all that kind of stuff, and they try to work academia into sort of a fluid situation where you can talk to other people. Otherwise, you're locked out. It's absolutely locked out. And I posted all my papers up there. I have 45 papers, and long ago. Although I did do this update, I don't know, a few years ago, I think. I can't even remember. But I am thrilled, and I thank you very, very much. Thank you, Academia. I really appreciate that. Okay, you heard the podcast by Richard Price, and he was talking about him. He's the CEO of Academia.edu, and he did a good presentation of my work. Not 100% exact, but as close as anybody. Now, this is the anatomy of a proton. It's not what they always thought it was, one big ball, and you could smash it into bits. And they found the tiniest little bits were these glowy parts and the black parts. And they didn't realize it, but they did get down to the smallest bits that exist. And to make protons and all matter, you just get bigger and bigger balls of this. The black goes to the center. It's just what happens. When you form molecules, it's a little bit different. You have to break into the crust of other molecules, and they share the crust. But you still have a black core in the thing that's sharing. All right, it's not hard to understand, really. It's very, very simple. And 1839 of these dipoles, which is the black and the glowy one, they can glow any color depending upon how intense they are. And we can make them glow completely, brilliantly white, which is, they don't get any more intense than that. And that's what we did do. And there's 1839 dipoles in a proton, which wants one more or wants to give one up. And there's 1840 in a neutron, which doesn't want to do anything. It's happy out by itself. Now, these are the only two particles that exist. He covered it pretty good. These are the only two. This one has all the energy and no weight whatsoever. Basically, it's just nothing more than fields. It's just like you take two magnets and push them together. If they oppose each other, you feel it. Feel like they're hitting a wall. But there's nothing there. That's what this does. This is just a pusher. It's of dark matter. That is dark matter, literally dark matter, and it creates all the gravity because it wants to pull in anything that has white attached to it. The Earth and us are primarily made of dark matter. This has no weight, nothing. You can just go like that through it. It's just there, but it's just like there's just nothing there. This, you just boom. That's solid mass. And when you put them together, they glue together. These two, which can be separated, which we did, are normally in this configuration, which is heat. That's heat. And it migrates into things and sort of drifts around inside of things and warms them up. And when it gets colder somewhere else, they just move to where it's cold. It's an attraction of the dark matter. It's a little hard to explain, but the hotter something gets. Hold on one second. You see this? I can guarantee you this is not correct. I asked, does solid matter gain weight when it gets hot? They say no, that's wrong. It suggests that heat has mass, so it should theoretically get heavier. The difference is minuscule, practically unmeasurable. It is measurable because I worked with the weights and measures to have my weights certified, and you had to leave them there over 24 hours so that they became the same temperature as the ambient temperature in the room. Otherwise, the weight wouldn't be correct. So they could measure it. So this is totally wrong. And other ones, they understand it. There's other ones down here. A hot iron is heavier than a cold one. True or false? It's true. Is a hot object heavier than a cold one? Yes. If you have absolutely identical objects, one of them's heavier, it weighs more because it has more heat inside of it, and heat is electrons. Electrons have a mass. It's as simple as that. This is not hard to understand. There's 1,839 of these in one proton. So the more heat you push into an item, I don't care what it is, the more it will weigh because it has more of these, and every one of these is 1/1839th of a proton. So if you flood that with heat and it gets really hot, you're going to have quite a few protons mass in there. Negligible, yes, absolutely negligible. But it was enough that I had to leave my weights overnight, and I wasn't happy because I thought I was just going to be able to bring them up, have them weighed, and bring them back. I had to go back the next day. And I still have it. I have a seal and stamps, and I had a license, and these lead seals that we could seal the caliper so nobody could change the thing when it went out in the field. And they hooked up to cash registers and stuff. That's the kind of business I was in. Point of sale stuff. So he said we had shots of it. Yes, we do. And I can show you these particles. That's a photon. Light creates photons. Photons are not like heat. Heat it gets absorbed into something. It wants to attach to something. This wants to bounce off of something. This has a big field around here, so it just wants to bounce off. This one doesn't have that. This has an attraction field or a repulsion field, depending upon if it's going into something colder or something hotter. And I can prove this with a Crookes radiometer. All right, it depends. It can go this way or this way, the Crookes, depending upon how you angle the light, whether you're hitting black or you're hitting white. If you're hitting white, it'll come back. I'm not kidding you. If you're hitting black, it'll push it that way. That's how a Crookes radiometer works. It hasn't been explained for 150 years. I think I understand it. And it's because it's in a partial vacuum. That's also part of it. There's a glass dome around it. That's part of it. This is a photon. That's a photon of light. And if you take 1,839 of these, which is 920 or so of the photons, add them together, you have a proton. Protons get bigger and bigger and bigger, and they create all kinds of different materials. And that's all they are, is just bigger and bigger, bigger balls. Now, and they get stable at certain places, and that's hard to explain, to be perfectly honest with you. There's something called resonance frequency. And everything here is magnetic and bouncy. You bounce into these things, they bounce like that. Now, to make bigger and bigger and bigger atoms, you need more and more and more and more particles. Now, I believe these are created by enzymes in biology, because they can't account for these heavy metals. There's no way they can account for them. But you can account for them using isotopes. That's a whole other issue. But it also is covered in dipole electron flood theory, the isotopes. Right now, they don't understand isotopes. If you only had gluons and protons, how do you get all these different half-lives? And I mean, there's literally thousands of them, because they're created by isotopes, which means you're only missing a couple of these. You're not missing a whole proton or a whole neutron. You're just missing some of these. And at a certain point, you get to so many missing that you drop down into the next lower one. And it's sometimes when they're getting so hot and under so much pressure, they can jump up. And a lot of that is done by enzymes. Enzymes can make billions of years worth of chemistry happen in less than 1 second. Look it up. How fast does an enzyme catalyze something? How fast does it break down and change the molecular structure? It can do up to billions of years worth of chemistry in less than 1 second. And the only place you get enzymes from is bacteria, and bacteria create the enzymes. The enzymes do the chemistry primarily in creatures' bodies. They can be good, they can be bad. It depends on what the bacteria does. Most bacteria breaks down food and creates good things for you. You got some bad stuff. And you got to have that most of the time. You do have bad stuff in you. Everybody has it. And the only reason it's there is to clean up the goop and eat up dead cells and things like that. But they have to be turned on in such a way that they don't eat up the good cells. And you have to have chemistry and enzymes in there to make every single one of those things happen. And if you don't have enzymes in your body, you will die almost instantly. You take one step and you're dead. And what happens, the enzymes are made by the bacteria. The bacteria are killed by radioactive pulses. You don't get sick. You know, nothing happens to you when you get that pulse. You just walk around and say, wow, that wasn't too bad. And about an hour later, you start throwing up, having diarrhea, having, all kinds of gut issues, bloating, and because you killed all the bacteria in your body and it's not creating enzymes. That's called acute radiation sickness. And it doesn't hit you right away. It just takes an hour, 2 hours, whatever. And how much bacteria was killed and how strong your body is depends on whether you recover or not. That's what nuclear acute radiation sickness is. All right, I'm going to show you some of the pictures he was talking about, but everything basically changes. Chemistry changes, as I just showed you. Space, time, and distance changes because the magnetic fields push back against particles coming in. They slow them down. You could speed them up. We speeded them up and separated the black from the white. So space, all that stuff changes. The redshift is just nonsense, basically. Light slows down. It doesn't travel the same speed. And this was done for me by Oscar Rosales, good friend. Dipole electron flood theory, excellent job. And it makes it just very, very simple to understand. Neutrinos, as they gain weight, they create flavors. The different colors are flavors. Once they achieve their full capacity, whether it's red, blue, or green, then it's locked in. And that becomes a photon of that particular light, that particular frequency. And I originally had two models. I had this one here, and then if you click this, it shows the first model I had. I've gone away from this. And I'm pretty sure that it is the black completely goes to the center, complete. And then the blue is really tight, which is what this other one here, watch. All right, the blue is the tightest particles. When you see blue going, you know you really, really rip that off of there, because you can't make blue go until you really slam it. It stays tight. Green, not so tight. Red is kind of loose. They know this, because when they hit them, the blue they see go and it never comes back. The green they see go and rarely comes back. The red, it almost always comes back, because it just doesn't have enough energy to just go flying away. It's still going to be pulled back to the to the black. So that's the anatomy of the proton. This is dipole electron flood theory. It works for everything. It works for gravity. It works for, there's nothing it doesn't work for. If you can come up with something, I want to hear it. That's why I want to have a discussion, and I want to have an open forum about this, and I'm hoping Academia.edu will engage and put out a word to all of these places, because apparently they service 15,000 universities with papers, and they track all this stuff and put it together, who's talking about who and who's saying what about what. And if I can just get an open forum in, a few hundred people to see this that are in that realm, I'm going to be good. I can't get it to anywhere in that realm. I can't get there, because they consider me a pseudoscientist. That's why I can't publish anywhere. And that's the beauty of Academia.edu. They let me publish. And now it sounds like they're pushing my stuff. That's pretty nice. I had not expected that. Now, could this lead to something? Yes, it could. It could lead for free energy. If we can speed this laser or shoot the laser, which we can, I've done it. It's done. It's already done. And at the Venturi, the black separates and the white showers completely by itself, which means you have ripped that white away. Just like they're doing with the head-on collisions. We forced all of those fields to get restricted and kept the black back. This is what you want, is the white. It has no weight. And you should be able to put a ton of lasers in here and create just gobs and gobs of energy from something this big. I mean, gobs. Have any kind of outlet you want. Not attached to the grid. No danger of anything. You're only working with light. It reattaches back here. I don't think there's any danger to those particles hurting you, because there's just nothing more than light. It's kind of hot at this part, but out here it creates a ball about that big. So this far away, it's not going to be dangerous anymore, I would say. And you could put some shielding inside the box and so forth. Anyway, this would be absolute revolution to the world, to be able to carry this around and pump water and fight fires and go into the woods with camping and whatever you had to do to protect yourself and save yourself. I'm telling you, we're in for some bad times. Now, not only that, this emits no problems whatsoever. It's energy neutral. I mean, it's atmospherically neutral. There's no gases emitted, nothing. When you take a car and you fill it with electricity, it never changes weight. If you got a 2,000, or let's take 4,000 pound car, because because they're heavy. And you fill that with energy, it's 4,000 pounds. You drive it all day long, you can't go any further, it's 4,000 pounds. You fill it all the way back up, it's 4,000 pounds. The energy in the white part is almost, it's just nothing there. And from the atomic bomb blast, I've shown it over and over and over. The house just burns up like this. And then the black particle comes and hits it. And I can show all of this stuff from the experiments we did. All of it. And light spins, just like he said, light spins. It doesn't flap like a wave and do this and that. It's spinning when it goes through. Pretty obvious. That's a single slit. I believe. It could be a double slit. It doesn't matter. But you need to filter it in. You can't have a flat plate like this because it just screws through. And it looks like it does this on the other side because they use two slits. But this experiment was designed to prove somebody's theory, and nobody ever really contested it. Well, I'm contesting it. Light spins, and I show this in 100 different shots. Rod Warren and I did a ton of this. I didn't do much, he did most of it. Now, this is the particle coming down, and originally it was just a nice wave like this, and you didn't even see it. See up here, you don't see these, but you see them here because it's being pushed back. All you see is the leading edge. This one you see because it's being pulled forward due to the Venturi. And right about here, they reassociate to the black, and they turn back into basically what they were on this side. They turn back into fields. They're always fields when they're together, or when they're either real hot and exploding, they come back into fields, or when they're being sucked away, you can see it. And this is the particle as it just is starting to accelerate. These waves are all over here. They're here, all over here, but you don't see them. You can't see them because they just sort of moving enough where they're getting through the atmosphere, but they're not fast. This is accelerating. Back here, it's just, you don't see it. It's not accelerating. Here it's starting to accelerate. You see it? And it's the tip of the wave is being sucked forward, and all of a sudden it's getting closer and closer to the Venturi, and zip, right through. It pulls itself right out of its own magnetic field. That's a magnetic field line. This is accelerated already. You shouldn't even see it. They're all over here. But you see them here. And the only reason you see them there is because it's bouncing backwards. And that's where this one lights up too. It's not lit up here. It's not quite advanced enough to think it's a photon. Here, it thinks it just hit a wall because of the bouncing back. And it thinks it hit a hard wall. You see how bright that is? That's because of the bounce back. Up here, there's just nothing because you don't see it. But right at the explosion zone, which is just a complete zone of explosion. Now we have to harvest that white right there before it hits back to the black, and then use a floating ground to bring it back to the black. And you will have gobs and gobs and gobs of electricity that you can carry around in a little lunchbox. It's as simple as this. It comes from the Venturi. Now you have to engineer the Venturi right. Very simple to do, actually. And then you have to pulsate the laser correctly, which is also seems to be quite simple. And when it comes through the shower cone, you have to sort of house that and put in, just like a solar panel, basically. But they have new thin film transition metal receivers that I think would going to be CMOS type of stuff that will absorb every different frequency of light instead of just getting one or two or three. There's a ton of different frequencies. White light is all the frequencies basically. So you want to collect them all. So, and then you want to shoot this down. See these different colors? That just means different transition metals. Transition metals are in here, and they have different charges on them. So they will absorb different frequencies. One of them will charge this, and one of them will absorb that, and one of them will absorb this. And you want to get them all, shoot them down here through the photodiode, which a photodiode means light, diode means go one way, and then there's a gate, don't go back. Once it's out, you use anything you want. You just plug into it and use it, or you can put it into a battery. Regardless of how you do it, you've got to come back to the floating ground. So you either go through your device back to the floating ground, or you got to go back to the floating ground, I would say. Although you might be able to discharge to ground itself. I don't know. I think you should be able to discharge the ground itself. Yeah, I would say that. I got to think about it, but I don't see why not. It's looking for dark particles. And the dark particles are on the other side of this, like a block of copper or something. But dark particles are in the earth, too. It's just like you took electricity and you put it into ground, right into ground. So you'd have to make sure that this was well designed so that the floating ground kept it floating inside the device and didn't let it come out through you to ground, because the amount of energy this thing should produce is just staggering, absolutely staggering, if it works the way they say. And it sure as hell looks like it. That's a lot of increase. Luminosity means energy. It started with none, it ended with pfft. And that's the energy you want. You don't want the black ones. You want just the white, and it has no mass. Those are the photons. These are the neutrino flavors. They haven't fully formed into a photon. A photon is just exactly like that. But I don't think you can get a photon until it really concusses. And here it thinks it's concussed because of the pushback. So we're seeing these photons floating in air because of the magnetic field that's slamming back against that magnetic field. That's what creates glow. Two magnetic fields slamming against each other. And as these particles come through the air, they sweep everybody else out of the way, and they make all those other little particles glow a little bit, but not crazy. You see all those particles? Those are gases and so forth that are in the air. Maybe moisture, I'm not sure. But these are telling those fields, get out of the way, get out of the way. I'm coming through, and I'm strong, and I'm glowy, and you're not as strong as me, so get out of the way. And it comes through and it pushes them, and they glow a little bit. All right, once it gets past them, they just don't glow anymore. You see back here? The glow is gone. The glow is over. But in front of them, all the ones in front of them say, whoa, here he comes, get out of the way, get out of the way. And once they're out of the way, they don't glow anymore. This is interesting to examine when you do examine it. When you just, oh, that's just interference. That's no, and that's exactly what I got over and over and over, every single place. Although I did go to the University of Geneva for particle physics online through Coursera, and they could not dismiss this. And they ended up using CMOS, which is what we use to see these particles. They ended up upgrading CERN to use CMOS. Because this is what they say right here. Muon neutrinos are the black balls. That's the black balls. Electron neutrinos are the white balls, and they turn into electron showers. When you hit heavy water, it's called Cherenkov radiation. And these are the particles, and they separated. That's fission and that's fusion. There's no other way to say it. It's subatomic, but it is fission when something breaks apart, and it's fusion when something comes back together. Here's where it broke apart, here's where it came back together. Simple as that. And these are Fermilab found this exact identical particles, but they found them in a pile of debris. The black with the glowy edge. The black with the glowy edge. Sounds like some kind of a book. And there she was, the black with the glowy edge. I mean, And these are just the balls of energy. They have no mass. Exactly what Don Lincoln from Fermilab says. He says there's just almost no mass whatsoever, but they have a strong field. And this has all the mass. And it doesn't radiate. But dark matter does not absorb, it doesn't emit, and it doesn't reflect. It's just there. And the only way you can see it is if it gets on top of the white, and that's exactly what happened with ours. The black you can see because it's on top of the white. It's just obstructing the light. It doesn't absorb, it doesn't emit, it doesn't reflect, but it obscures. Like this is on top of the white too. The only reason you can see them. There's black particles everywhere around here. They're every single place around here, black. But you don't see them until they get right up, hugged up close to the white. It's just the nature of the particle. It's dark matter. They know this. Nobody's going to discount that. And it also creates gravity because it's attracting all these white particles. And everything that has mass has white particles. The white particles surround the black. So anything there is has like these energetic little particles surrounding the core, which is the dark matter. And it's surrounded by the white matter, so we've never seen it. Anytime you shine light at that, all you see is white matter. You think, well, all that is white matter. But no, inside is the dark matter. It's gravity and it's dark matter. And as it's traveling through space, it's a particle, and these things here bounce other particles away from them, and they glow them a little bit. And when they glow them, they slow them down. They don't stay the same speed. Here's the green. Same deal. It's coming through. These are the neutrinos. You see this thing with the white and the black on both sides, and then this one here with the black and the white on both sides. That's the different flavors. And this is the photons. This one here is a downspin. When the glowy part is down, it's a downspin. And they will always be polar to the Earth. No matter whether they're going this way or that way, they'll spin only according to straight up and down. That's why they call them up and down spin. Now, as they move forward, you see this? That's the downspin part charging up. It's getting strongly charged. And if you look carefully and just take your time and think, you can see this is whiter. Whoops. You can see this is a little bit brighter than that. And it's charging, and in a second, it's going to flip. And this side will come forward. Then it will be an upspin until that charges and it flips. That's called a muon wobble, oscillation. There's no way they can explain that either. They see it. They just don't understand it. It's oscillation, and it's because of charge, discharge, charge, discharge, charge, discharge, as it moves forward. And it's always straight up and down, even though it's going that direction. If it's straight across the horizon, it's straight up and down, like the red one I showed you. But even if it goes this way, it's still straight up and down. And that's because of the polarity to the Earth. Now, what haven't I shown you? Not much. I got so much stuff here that just is not understood by mainstream science that there's a lot of things we're going to have to go over. It's not just this. The dipole electron flood theory is what before you can even start to understand chemistry or isotopes or bonding or any of that stuff. They do to some degree, because some things are quite obvious, but there's the isotopic half-life scenario where enzymes do that is not understood, and it can bump something up to make it a bigger atom, or it can drop something down. That's called the decay. Usually you think of it going down when they say decay, but decay can also go up if it's under pressure and a lot of electrons are forced in, a lot of dipoles. When a lot of extra dipoles are forced in, you end up with a bigger mass and a different molecule. The nucleuses can change. They say, oh, no, you can't do that. Yes, you can. Absolutely, you can. Absolutely, you can. All right, I work a lot with phosphorus because it is the membranes that were in the mud fossils. Now, I find some bump up to sulfur and some come down to aluminum silicates. And it's related to half-lives, and it's related to the chemistry they were in, the pH, the heat, the temperature, the compression, how long they were in, the chemistry, the transition metals. All of that stuff plays into the half-life and what these things end up being. But the phosphorus is in the phospholipid membranes. Now, this is going to be simple, so don't get crazy. It's very simple. When you take phosphorus and you look it up on a periodic chart, each one of these is another proton. They say 1 and then 2 and then 3 and then 4 and then 5. Well, and then they throw in a bunch of neutrons because they can't account for some of the weight, so they throw in a bunch of neutrons. Now, when you get up to phosphorus, you got 15 protons, but it's nowhere near 15. 15 protons is just silly, because here's the Z number is protons. Atomic number of nuclear charge. All right, proton number has nothing to do with neutrons. So they're all 15. All of these different phosphoruses, and they're all different. I thought there was just one phosphorus. No. Then they take neutrons, and they take this neutron, 11, 11, 11, but then they give them different little attributions. This one can turn down to a silicon from phosphorus, which is 1 down. Phosphorus decays. They call that the daughter isotope, which means you started with this, and something happened to make a particle come away, and you end up with silicon. All right? This next one up, which is basically the same thing, I don't see how they can have 15 and 11 and have something different. It's basically exactly the same thing, but it goes up to aluminum. Down to aluminum, one more under the silicon. And then they have another one that goes down to magnesium, way down to here. And they're all three of them supposed to be 15 protons and 11 neutrons. It makes no sense whatsoever, none. They're all basically identically the same, but they decay different. Now, then you start coming up to 12 and 13 and 14, and each one of these is another neutron. For me, another neutron is 2,000 more particles. So the amount of variations in half-lives is just staggering. Because instead of this being 11, that's 22,000. All right? Instead of this being 15, that's 30,000, approximately. All right, so they're talking about these little half-lives and this happened, that happened, and we know that's a half-life. No, there's a half-life can go 1 more, 2 more, 3 more, 5 more, 10 more, 50 more, 2,000 more, 5,000 more, 8,000. You can have thousands and thousands and thousands. And it can happen so fast that it's being done millions to billions of years of chemistry in under a second, because you have the enzyme. It's called click chemistry. The enzyme is a particle it's so exotic, it's amazing, and it comes up and it goes click, 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 click. It doesn't get used up. It just goes click, 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 and thousands and thousands of particles change into something else instantaneously. So now we're below stable. This is what they call stable. All right, these decay downwards. Well, now we're decaying upwards because we're going above stable. So stable is right here. Well, actually, let's do it this way. Stable is this number of particles. Well, these are some of these missing. And the more missing, the further down you go, the less they weigh. It's quite obvious, and this is the atomic mass. So now, here we are at stable. Well, under heat and pressure, you're going to be forcing electrons in. Well, what does that mean? Well, 1 or 2 or 3 will force their way in. And they'll force their way in because it's pressure, and it's heat, and it's pH, and it's time, and it's fluids, and it's nucleophilic invasion. And what happens? From stable, instead of going down, it goes up. Phosphorus goes up to sulfur. I'm making you a chemist right now. I'm making you a physicist, and you're going to be as good as anybody right now because they don't understand that. They don't realize there's so many particles in between here. It's staggering. So not only are these particles something, these are the only ones that they can claim. I don't know how they claim them, because they happen pretty fast. But these are in seconds. Some of them are in days. Some of them are in minutes, milliseconds. We want ultra tiny second, because it does 100,000 millions, billions of connections in less than 1 second. So they're never going to see those ever. It can't be seen. That's how they bump these particles up. I call it atomic bump. The more they go to sulfur, now what's going to happen from the sulfur? The sulfur can keep going up. If I go to sulfur, I can see this, and all these are sulfur. And this one comes back to phosphorus for some reason. I don't know why. The biggest one. That one there confuses me, but I don't care, because it doesn't matter. And you can keep bumping and bumping and bumping and bumping, and they don't have any explanation for these heavy metals. All they can say is, well, it must have happened in the Big Bang, which is another serious topic of discussion.